In this lesson, we're continuing preparing for the probability state standards 1 and 2. So our objective for today is to find the probability that an event will occur. So let's go back to the idea of flipping a coin. Remember from our previous example, our sample space contains two elements. You can either get a heads or a tail. And we said that these two outcomes are equally likely to occur. So therefore, the probability of getting a head, which we'll represent by p sub in parentheses h, is equal to the probability of getting a tail, which we'll represent by p and then in parentheses t, and they're equal to each other. Probability of getting heads is equally likely as getting a tails, and the probability for either one is 1 out of 2. When we go back to the die example, they're the standard six-sided fair die. There's 6 possible outcomes. You could roll a 1, 2, 3, 4, 5, or 6. Each of them are equally likely. So the probability of rolling a 1 is the same as the probability of rolling a 2, which is the same as the probability of rolling a 3, and the same as the probability of rolling a 4, and the same as the probability of rolling a 5, which is the same as rolling a 6, and the probability of each and every one of those is 1 out of 6. Remember, again, in both of these cases, it's your favorable outcome, whether it's a head or a tails, the possible outcomes. Rolling the die, your favorable outcome, whether it's a 1 or a 2 or a 3 or 4 or 5 or 6, there's one of those outcomes out of the 6 possible outcomes. So again, probability is still your desired or favorable outcomes over the possible. So to generalize, because maybe some of you have a standard, well, not so standard die that has more than 6 sides. So in general, if a sub 1, a sub 2, a sub 3 through a sub n is a sample space representing n equally likely outcomes, the probability for each simple event is 1 out of n. I don't know about you, but I've actually seen someone with a 20-sided die. So if that were the case, the probability of rolling the number 1 or the number 20 or any number in between would be 1 out of 20. And each probability would be equally likely. Probability of a sub 1 is the same as the probability of a sub 2, etc., etc., is the same as the probability of a sub n, which is 1 out of n. So 1 if you're getting one favorable outcome over n total possible outcomes. So let's get to another situation. Unroll a single die. We're going to let the capital letter A represent the event that we get an odd number. So the odd numbers from rolling a standard fair six-sided die is 1, 3, or 5. Our sample space is 1, 2, 3, 4, 5, 6. And we can represent the probability of A as the sum of each simple event. So the probability of getting a 1 or a 3 or a 5 is the probability of rolling a 1 plus the probability of rolling a 3 plus the probability of rolling a 5. Each probability we said is 1 out of 6. So the probability of rolling a 1 is 1 out of 6. Rolling a 3 is 1 out of 6. Rolling a 5 is 1 out of 6. We're going to add those together, which gives us 3/6 or 1 out of 2. So we have a 1 out of 2 or 50-50, 0.5, 50% chance of rolling that. So if we generalize that, in general, if there are n equally likely outcomes, and if we have k of them in the event that we're looking for, just like we had 3 choices here in rolling our odd number, 1, 3, or 5, we're going to find the probability of that event by the probability of getting each one that we're looking for and adding the results together, which in general gives us k over n. So just like in this numerical example, we had 3 over 6. It could have been a 1 or a 3 or a 5 that we rolled. So we had 3 out of 6. Here it'll be k out of n if we generalize that. And again, I know we said this in the previous lesson, but let's come back and visit it. If the event E contains every element in the sample space, then the probability is n over n, or 1. If we say percentage, 100%, and we say the event is certain to occur. If the event contains none of the elements in the sample space, then the probability of that is 0 out of n, or 0, and we say the event is certain not to occur. So for example, if we were rolling a standard six-sided die, and you said, what's the probability of rolling a 7? Well, that's impossible because there's no 7 on a 1 through 6 fair standard six-sided die. So the probability would be 0 out of n, or 0. Right, and again, once more, the probability of any of our events have to be greater than or equal to 0, less than or equal to 1. So let's look at a few examples in this particular case. We roll a single die, find the probability of each event. Event A says that the number showing is less than 5. Well, the sample space to represent that is a 1, 2, 3, 4, which the probability then, therefore the probability of event A, is the same as the probability of rolling a 1, or rolling a 2, or rolling a 3, or rolling a 4. So we're going to add them all together. For right now, I'm not going to talk about addition rule or multiplication rule other than just mentioning their names. But in this case, it's pretty much saying we're rolling a 1 or a 2 or a 3 or a 4. You can pretty much replace the word or with addition. So we have 1 out of 6 plus 1 out of 6 plus 1 out of 6 plus 1 out of 6 gives us 4/6, or a 2 out of 3 chance of rolling a number less than 5. For the second event, event B, the number showing is between 2 and 6, not including 2 or 6. That gives us a 3, 4, or 5. So the probability of event B, therefore, is the probability of rolling a 3, or probability of rolling a 4, or probability of rolling a 5. So that's 1 out of 6 plus 1 out of 6 plus 1 out of 6, which is 3/6, or 1/2. All right, let's roll 2 dice and keep track of what we get. Let's look at the probabilities of these events. Event A, the sum of the numbers is less than 5. Event B, the sum of the numbers equals 4 or equals 5. So again, remember from our previous lesson, we're going to say the possible outcomes. We're going to use ordered pairs to represent the 2 die. We can go anywhere from a 1 with a 1, 1 with a 2, 1 with a 3, all the way out to a 6 with a 4, 6 with a 5, 6 with a 6. 36 possible outcomes when rolling a pair of dice. And so when we look at the sum of the numbers is less than 5, here's event A. You can get a 1 with a 1, 1 with a 2, 1 with a 3, 2 with a 1, 2 with a 2, 3 with a 1. Those are less than 5. And so there are 1, 2, 3, 4, 5, 6 of those possibilities. So in our previous lesson, our favorable outcomes over our possible outcomes, 6 out of 36, or 1/6. For event B, we have to equal a 4 or 5. So 1 and 3 is a 4. 1 plus 4 is 5. 2 plus 2 is 4. 2 plus 3 is 5. 3 plus 1 is 4. 3 plus 2 is 5. 4 plus 1 is 5. Those are the possible ways to get a 4 or a 5. So in that case, there's 1, 2, 3, 4, 5, 6, 7 favorable or desired outcomes over 36 possible outcomes. So the probability of event B is 7 out of 36. All right, for a moment now, we're going to get away from rolling dice and focus on this particular problem. If we have 12 tulip bulbs in a package and 9 of them will develop and grow into yellow tulips, 3 will yield red, and if 2 tulip bulbs are selected at random, find the probability of each event. So if you think this sounds similar to the probability of taking marbles out of a bag, pretty much sure. So event Q, what's the probability of both of them being red? Event R, what's the probability of one being yellow and the other one being red? So let's take a look. Since we are selecting these bulbs at random, all possible outcomes are equally likely. So probability of event Q, both will be red, are the number of ways to choose 2 red bulbs, that's our desirable or favorable outcomes, over the number of ways to choose any 2 bulbs. Now, I'm emphasizing the word choose because we talked about this the other day. Remember, choose or select is the idea of combinations. So we're going to take the number of ways. There are 3 that will give us red tulips, and we are going to choose 2 of them. That is going to describe our favorable or desired outcome. And then the total possible outcomes is there are 12 bulbs in total, and we're choosing 2 of them. So again, 3 choose 2 using our formula for combinations. That's 3 factorial over 3 minus 2 factorial, which is 1 factorial, times 2 factorial. 12 choose 2 is 12 factorial over 12 minus 2 factorial, that's 10 factorial, times 2 factorial. If we simplify that, 3 factorial times 2 factorial, the 2 factorials divide out, we just get 3. 12 times 11 times 10 factorial, the 10 factorials divide out, and then we end up with 66 because we've got 12 times 11 divided by 2, so 6 times 11 is 66. And then reducing that, we have a 1 out of 22 chance that both tulips will be red. Now the second part of our problem says 1 yellow and 1 red. So I'm emphasizing the word and here for a second because that's going to imply informally for now multiplication. So let's look at our favorable or desired outcomes. We've got 9 bulbs to choose from. Let's go back and look at it. 9 will give us yellow, and then 3 will give us a red tulip. So we've got 9 yellow, choose 1, times, because it's and, compound event, 3 choose 1, that's our numerator. Denominator still 12 choose 2, and since we just calculated 12 choose 2, we know that's still going to be 66. So let's take a look at this. 9 choose 1 using our combination formula is 9 factorial over 9 minus 1 factorial, which is 8 factorial, times 1 factorial, times 3 factorial over 3 minus 1 factorial, which is 2 factorial, times 1 factorial. Our denominator is still the same, so I won't go through that again. Let's try to simplify our numerator some more. 9 times 8 factorial, the 8 factorials divide out, we're left with 9. 3 times 2 factorial, the 2 factorials divide out, we're left with 3. So we have 27 out of 66, or if we reduce that, 9 out of 22 possibilities of picking 1 yellow and 1 red bulb. All right, let's go back to a deck of cards. If we choose 2 cards from a deck of 52, what's the probability that both of them are spades? So we're going to get down to the probability rather than using a capital letter to represent the event like we did in the previous cases, the probability of event R. Some books, some teachers will write it out. So let's write it out. Probability of getting 2 spades is the number of ways of getting a spade over the number of ways of selecting 2 cards. So again, select, choose, that's our combination formula. And I'm writing combinations in that different notation, so you can get used to both of the notations. We use this notation in Chapter 11 for the binomial formula, binomial theorem. So we're going to take, there are 13 spades, and we're choosing 2 of them. That's our favorable or desired outcomes. And there's 52 cards, we're choosing 2 of them. That's our denominator, our total possible outcomes. So 13 choose 2 over 52 choose 2. Excuse me. So that's 13 factorial over 2 factorial times 13 minus 2 factorial in the numerator. Denominator is 52 factorial times 52 minus 2 factorial times 2 factorial. So 13 factorial, we're going to write that as 13 times 12 times 11 factorial and stop, because 13 minus 2 is 11 factorial, and those will divide out in just a second. 52 factorial we'll write as 52 times 51 times 50, and we'll stop there because 52 minus 2 is 50 factorial. And as we said, the 11 factorials will divide out, the 50 factorials will divide out. 12 divided by 2 is 6. 52 divided by 2 is 26. When we continue that, our numerator is 13 times 6 for our favorable outcomes, and then 26 times 51 for the possible outcomes, which gives us 78 over 1,326, and that reduces to a 1 in 17 chance that if we randomly select 2 cards from a deck, that both of them are spades. All right, here's an alternate solution. And I'm going to lead up to this because I haven't really discussed it yet. It'll be in our next lesson. But some of you might think of it like this. There are 13 spades when we choose the first card. There are 52 cards. So when we choose the first card from the deck, thinking of this as a compound event, we have a 13 out of 52 chance that the first card will be a spade. Now, once we've taken that card from the deck and not return it, now there are only, and if it was a spade, there's only 12 spades left, and there's only 51 cards left in the deck. And if we multiply these together, 13 out of 52 reduces to 1/4. 4 will divide into 12 3 times, and that leaves us with a 3 out of 51 chance, or a 1 out of 17 chance for drawing 2 cards randomly from a deck and getting both of them to be spades. We'll talk more about this alternate solution. It's the idea of dependency in our next lesson, but we're still pursuing state standards, probability state standards 1 and 2, and we're just delving into calculating probabilities that certain events will occur.